Welcome back to the course Basics of Mechanical Engineering 3. I am Dr. Amandeep Singh Oberoi from IIT Kanpur. I am going to discuss psychometrics in this tutorial 4. Psychometrics, which is the science of moisture, I would say science of moisture, or the thermal science when we talk about, or thermodynamics when we talk about the properties of moisture. It could be temperature, it could be humidity, it could be properties which are associated with the moisture, and there is a psychometric chart that was shown in the lecture. I will just try to recall the concepts and try to take some problem statements. So, in psychometrics, first part I will try to cover is gas vapor mixtures. To calculate the volume occupied by a given mass of saturated water vapor, V1 is equal to M1 into Vg, where it directly relates to the mass of water vapor, Mv, its specific volume, Vg, which is volume per unit mass at a given saturation temperature. Ideal gas law for partial pressure of air, that is, for air, the partial pressure is N R bar T by V. These variables, you know, this is P is pressure, T is temperature, V is volume, N is a constant, and R bar is universal gas constant. We are talking about partial pressure of air. This is for ideal gas law. PV is equal to nRT, you have studied multiple times. Now, when we convert this into M by M, that is small m for air by capital M for air, that is to the mass of air to the molar mass of the air, that is N, that is mass of air to the molar mass of air. This relationship comes as M air R bar T by M air V, which is capital M in the denominator, which is molar mass of the air. Now, total pressure of container, that is given as total pressure, that is the pressure of air plus pressure of vapor. Because we are talking about the moist air here, if we are talking about a container, the formula is based upon the Dalton's law of partial pressure, which states that total pressure of non-reacting mixture of gases is equal to the sum of the partial pressure of individual gases. It is non-reactive mixture of gases, total pressure, and this is the sum of the individual gases partial pressures, P air plus P vapor. In the context of moist air mixture, the total pressure within a tank is the sum of the partial pressure of dry air and partial pressure of the water vapor, that is P vapor. This allows for the calculation of the overall pressure acting on the tank walls. Now, let me take a problem statement. A rigid tank contains a mixture of 0.2 kg of saturated water vapor and 2 kg of air. The molar mass of air is given as 29 kg per kilomole and R is given as 8.314 joules per mole Kelvin. You are given the following data at 50 degrees centigrades. Now, also we have been given is saturation pressure of water vapor, that is P sat is equal to 12.349 kilopascal, specific volume of saturated water vapor, that is Vg as 12.0318 meter cube per kg. Assume ideal gas behavior, that is whatever relationship that we have discussed for the ideal gas holds true here. So, for ideal gas we will use the relations. What is the total pressure inside the tank? So, P total is to be determined. So, what we have here is a tank in which we have air and water vapor. So, we have water vapor here, that is this is the gas kind of a system. In this, temperature is 50 degrees centigrade, it is given. So, temperature given is 50 degrees centigrades, which is equal to 273 plus 50 would be 323 Kelvin. Then we have gotten a mixture of water vapor and air. The weight of water vapor, I'll put it as M1. This is equal to 0.2 kg. And the weight of air is 2 kg. Then we have molar mass 29 kg per kilomole, that is capital M of air. This is equal to 29 kg per kilomole. Pressure at the saturation, that is P vapor, though it is given P SAT, that is at saturation pressure of water vapor is given, I will put it as P vapor because in the relations which I showed you in the previous slides, I have used it as P vapor. It is 12.349 kilopascal, and specific volume, that is Vg, V is put small here always because this is specific volume. For the regular volume we use capital V. For the specific volume, small v is given, which is 12.0318 meter cube per kg. Now, in this, at T is equal to 50 degrees centigrades, we have 0.2 kg of vapor and 2 kg of air. Now, total pressure inside the tank. To find the total pressure, let us first calculate the volume of saturated vapor. Volume of saturated vapor, which is V1, that is taken from this relation. V1 is equal to M1 into Vg. This is equal to M1 into Vg. Putting the values, M1 is 0.2 kg and Vg is 12.0318 meter cube per kg. So, I get this as 2.406 meter cube. Now, using ideal gas law, because what is the question? You need to find the total pressure. To find the total pressure, I already know the pressure of vapor. Total pressure is what? Pressure of air plus pressure of vapor. These partial pressures. Pressure of vapor is given. Now, pressure of air is to be calculated. Using ideal gas law, I will find pressure of air using this relation. Pressure of air is this here. This is equal to mass of air into R bar into T by molar mass of air into the volume, that is V1, that is volume of saturated vapor. Now, putting the values, I have 2 into 8.314 into 323 Kelvin by molar mass of air is given as 29 kg per kilomole. So, this is 29 into volume we have just calculated, which is 2.406. I get the pressure of air as 76.97 kilopascal. Now, total pressure total is equal to pressure of air plus pressure of vapor. This is equal to 76.97, which is calculated value, plus the given value 12.349 of the pressure of the vapor. This gives me the pressure total inside the tank as 89.31 kilopascal. So this was a simple problem when we talk about the gas mixtures. When air and vapor are mixed, how do we calculate the pressure? Ideal gas equation holds true here, we have calculated. Next, I will try to calculate the dryness factor and like to discuss the dryness factor before, then I will try to come to the calculations. When we talk about dryness factor, it is quality or dryness fraction. Dryness fraction is defined as the ratio of the mass of the vapor to the total mass of the mixture and is denoted by symbol X. This property is significant because in saturated region, the substance does not exist entirely as liquid or vapor, but as two-phase mixture, and the quality quantifies how much of it has turned into vapor. So this X is given as S2 minus FF, where S2 is entropy at turbine exit, SF is entropy of saturated liquid. Then we have SFG. F is fluid, G is gas. When we say SFG, it turns out to be entropy of vaporization. That is, SFG is equal to Sg minus Sf. Here, if I try to put some more light over how is this being plotted, I will draw temperature pressure curve here, and for a saturated liquid it is something like this. At saturated temperature, when X is equal to 0, here 2, X is equal to 1, somewhat here. So this temperature remains constant, that is the saturated temperature, but the saturated vapor flows in this fashion. For instance, it is something like this, going above, suddenly, then a little slower fall. What do we have here is, here it is saturated liquid, we have saturated vapor here. This is the mixture of liquid and vapor. I will call it as saturated liquid vapor. And exactly down there is also the saturated vapor only. So this line here is saturated pressure line. Now for enthalpy at turbine exit is given by H2, which is equal to the sum of HF and the product of X and HFG, where HF is enthalpy of saturated liquid, HFG is enthalpy of vaporization. Turbine work output per kg, that is the work done by turbine, is the difference of H1 and H2, that is H1 minus H2, where H1 is enthalpy at turbine inlet, H2 is enthalpy at turbine exit. So using these relations, let me try to see a problem statement. Steam enters a turbine at pressure of 3 megapascal and temperature of 350 degrees centigrade, expands entropically to a pressure of 100 kilopascal. The value of enthalpy and entropy at 3 megapascal and 350 degrees centigrade is 3115.3 kilojoules per kg and 6.7432 kilojoules per kg Kelvin. This is enthalpy and this is entropy. I should put a word respectively here. From saturated water tables at 100 kilopascal, SF, that is the entropy of saturated liquid, is 1.3026 kilojoules per kg Kelvin. SFG that is entropy of vaporization is 6.0569 kilojoules per kg Kelvin. HF, that is the enthalpy of saturated liquid, is 417.46 kilojoules per kg. HFG, that is enthalpy of vaporization, is 2257.9 kilojoules per kg. We need to determine the work output per kg of steam and the quality of X, that is quality X at turbine exit. So this is something, a situation where we have a turbine. This is a turbine and it turns steam into work. So we have inlet pressure and temperature that is given. I will call it as P1 is equal to 3 megapascal. T1 is 350 degrees centigrades. The outlet pressure is also given, that is 100 kilopascal. P2, that is the outlet pressure, that is 100 kilopascal. This is inlet, this is outlet. Also other parameters are given, such as we have H1, that is 3115.3 kilojoules per kg. We have S1 as 6.7432 kilojoules per kg Kelvin, and these four values also given at 100 kilopascal. Now we need to determine the work output per kg of steam. So part 1, that is work output. Output per kg of steam. For this, let me first calculate the dryness factor, that is X. Here X, using the relation, this is equal to S2 minus SF by SFG. This is S2 minus SF by SFG. Now because it is isentropic expansion, isentropic means entropy does not change, which means S1 should stay equal to S2. So I can put as S1 is equal to S2. So I can put in this relation the value of S1 itself, which is given as 6.7432 kilojoules per kg Kelvin. 6.7432 minus SF, that is given as 1.3026 by SFG. This value is 6.0569. So I got my value of X as 0.898. So that means I have calculated the second part of the question, the quality X at turbine exit here. This is X. This one part is over. Now for the next part, that is work output per kg of steam. For this I need to understand or calculate the enthalpy at the exit. That is H2. So this H2 is sum of two entities. One is HF, second is the product of X and HFG. This is equal to HF plus X into HFG. Putting the values, HF is 417.46 kilojoules per kg. X is 0.898 and HFG is given as 2257.9 kilojoules per kg. This gives me the value of H2 as 2445.05 kilojoules per kg. Now I can calculate the work output. Work output is equal to H1 minus H2, which is 3115.3 minus this calculated value of H2, 2445.05. This is equal to 670.25 kilojoules per kg. So this is work output per kg. That is work done by turbine. Let me see another problem statement. Here it says steam is expanding isentropically in a turbine from 80 bar to 7 bar. The inlet of the turbine has the following properties, that is H1 as 3246 kilojoules per kg, S1 as 6.52 kilojoules per kg Kelvin. Find the enthalpy of the steam exciting the turbine in kilojoules per kg. At 7 bar, the steam properties are also given. We have been given the values of HF, HG, SF and SG. It is very similar to the previous problem statement. Only here what we have is something like this. It is enthalpy versus entropy. So when we draw, they say the steam is expanding isentropically in turbine from 80 bar to 7 bar. So if I put H1 here and H2 here, and here it is something like this, because it is isentropic process. This will also go to this point in this way, and this becomes 0.1 and this turns out to be 0.2 because this is isentropic, and the curve would be somewhat like this. Going there and coming to 2. So in the psychometric charts, the curves would go like this. It will pass through 1, it will pass through 2, right? Because it is isentropic. Here S1 is equal to S2, like we discussed in the previous problem statement. Here it is not a big deal. You only need to calculate first value of X, which is S2 minus SF by SFG. This you will find, and you will find the value of H2. They say find the enthalpy of the steam exciting the turbine. That is H2 is to determine. H2 is equal to HF plus X into HFG. This I am also keeping it for you. All the values are given here. You need to put into the relations and calculate the value. And I will put the values and you can review your results with the notes which I will provide. Now, I will try to see another concept, that is partial pressure. Partial pressure of water vapor is the pressure exerted by water molecules in the gaseous state, that is water vapor, within a mixture of gases like air. It represents the contribution of water vapor to the total atmospheric pressure. So PV, which is the partial pressure of water vapor, is phi into P saturation, that is Psat we saw, it is saturation pressure of water vapor at a given temperature, where phi is relative humidity. So partial pressure is important factor, important point to be discussed and to be calculated. Partial pressure of dry air is the difference between the total pressure and the partial pressure of water vapor. So this also we can say here, because we know total pressure as we saw in the previous system here. Total pressure is pressure of air plus pressure of vapor. What would be pressure of vapor? It would be the total pressure minus pressure of air. So similar thing is mentioned here. Pressure of air, this is total pressure and this is pressure of vapor. Pressure of air is given in this way. Specific humidity ratio, that is omega is equal to 0.622 into the ratio of PV by PA, that is pressure, that is partial pressure of water vapor to the partial pressure of air. Enthalpy of moist air per kg of dry air, that is H is equal to Cpa into T, where Cpa is specific heat of dry air, whose value is that we have discussed 1.005 kilojoules per kg Kelvin, plus omega into the sum of HFG plus CPV into T, where CPV is specific heat of water vapor, whose value is 1.88 kilojoules per kg Kelvin. Let me see a problem statement and we will understand this better. A room contains air at 20 degrees centigrade and 98 kilopascal at a relative humidity of 85%. This is a regular room condition, maybe in the month of November or February, when winters are just coming in India, when the temperature is around 20 degrees and pressure is 98 kilopascal. Relative humidity is around 85%. If the saturation pressure at 20 degrees is 2.3392 kilopascal and HFG is 2537.4 kilojoules per kg, what will be the partial pressure of dry air and the enthalpy per unit mass of dry air? Take specific heat of dry air as this and specific heat of water vapor as this. These values I have given in the previous slide as well. So we need to find out partial pressure of dry air and enthalpy per unit mass of the dry air. So this is a room where temperature is 20 degrees centigrade, pressure is 98 kilopascal, phi, that is relative humidity, this is given as 85%. So we have air and water vapor both here. Now the given things are again temperatures 20 degrees centigrade, pressure is 98 kilopascal, phi is 85%, that is 0.85, P saturated is 2.3392 kilopascal and HFG is 2537.4 kilojoules per kg. Let me try to calculate the partial pressure of dry air and enthalpy per unit mass of the dry air. To calculate this, simply partial pressure of dry air could be taken from this relation. First we will find the partial pressure of the vapor and then we will find the partial pressure of the dry air. So first is partial pressure of vapor. Whenever I write vapor, it means water vapor here. This is PV is equal to phi into P saturation, this is equal to 0.85 times 2.3392, and this partial pressure of vapor is 1.9883 kilopascal. Now partial pressure of air, that is P air, would be the difference of total partial pressure and partial pressure of vapor. This is equal to, total partial pressure is given as 98 kilopascal. We have just calculated the partial pressure of vapor, that is 1.9883 kilopascal. So the partial pressure of air turns out to be 96.011 kilopascal. This is P air. So one part is calculated. Now they say find enthalpy. To find enthalpy, we need to first find the value of omega, that is specific humidity, and this omega would be used here to find enthalpy. So omega, that is specific humidity, this is equal to 0.622 into PV by PA. So this will be 0.622 into 1.9883 by 96.011, and this value is 0.0128. It is kg vapor per kg of dry air. That is specific humidity. Now let us try to find the enthalpy. H is equal to CPA into T plus omega HFG plus CPV into T. So this is equal to, putting the value, CPA is 1.005, temperature is 20, plus omega we have calculated, that value is 0.0128. This into HFG, that is 2537.4, then plus CPV value is 1.88, and the temperature is 20 degrees. So this value of H turns out to be 53.06 kilojoules per kg. So let me see another problem statement. Here it is given air at pressure 101.325 kilopascal and 30 degrees with absolute humidity of 0.0218 kgs per kg of dry air. Vapor pressure of water, that is P saturated, and temperature is given below. So this is a relation given. We call it a regression equation. Find the relative humidity of air in percentage to the nearest second decimal. Now what happens is, we have a drying chamber and air comes in, which is dried. Pressure here is 101.325 kilopascal. Temperature is 30 degrees centigrades, and we have been given absolute humidity, or we call it as specific humidity, which is omega as 0.0218. So we need to find the relative humidity of air in percentage. That is, phi is to be found. Given all the values, P saturation is given, we will just try to put this in the relation. In using this relation, where log of P saturation is this value, this means when we say log of x is equal to y, because this is natural log, so then it turns out as x is equal to e power y, where e is the exponential constant whose value is 2.71828. Now, putting the value of temperature here, you can calculate P saturation. That means P saturation would be equal to whatever the value turns out to be, e power this value, whatever this value would be. Because I am leaving this for you, I will just give you the relations which are being used in this here. Now, once you have the P saturation value, you can calculate. So, from the value of omega, which is 0.622 times P vapor by P air. So, this could be put as 0.622 into P vapor by P total minus P vapor. This will give you the value of P vapor. Right, from here you will calculate the value because omega is given, because value of omega is given in the question. Now you know phi is equal to P vapor by P saturated. You will find the value of phi. I am leaving this open. Next and the last part that we will cover in this lecture is phase change. Phase change, this is the heat required to raise the temperature of the liquid from its initial temperature to the boiling point. That is Qs is equal to m times Cpl into the difference of the temperatures, that is T boil minus Ti, where T boil is at the boiling temperature, Ti is the initial temperature of the liquid, Cpl is the specific heat of the liquid, m is the mass. Phase change heat could also be put here in this relation, that is Q of phase change is m times HFG. HFG is enthalpy HFG. This is the heat required. So, phase change heat is the heat required to change the phase from liquid to vapor at a constant temperature and pressure. So, for a sensible heating system, once again, if we need to find the superheated temperature, that is the heat needed to raise the temperature of the steam from a boiling point to the desired superheated temperature, that is QSH, this is equal to m into CPS, that is specific heat of vapor or steam, into the difference of TF and T boil. TF is the final temperature of vapor, T boil is the boiling temperature of the liquid. Because we are talking about phase change, we will put all properties of liquid also here. Now, let me see one problem statement so that we understand these relations better. Now, the problem says, how much heat is required to convert 2 kg of water at 45 degrees and 1 atmospheric pressure into superheated steam at 300 degrees centigrade and 1 atmospheric pressure? The latent heat of vaporization is 2257 kilojoules per kg. Assume the process includes sensible heating, phase change and superheating. Take the values of specific heat of water and specific heat of steam as 4.18 kilojoules per kg and 2 kilojoules per kg respectively. Now, we need to convert to the superheated steam from the initial condition when mass is 2 kg, temperature is 45 degrees centigrade, pressure is 1 atmospheric pressure, to the superheated steam that is at a temperature of 300 degrees centigrades and pressure is 1 atmosphere pressure only. I will put it as 1 bar. I will put bar here. So this is water and this is superheated steam. How to convert water into superheated steam in these conditions? So I have been given mass as 2 kg, temperature as 45 degrees centigrades, pressure as 1 atmospheric pressure or 1 bar. Then temperature TF is 300 degrees centigrades. HFG is 2257 kilojoules per kg. CPL and CPS are also given. CPL is 4.18 kilojoules per kg and CPS is 2 kilojoules per kg. Now putting these relations, that is QS, it is heat required to raise temperature to liquid from the initial temperature, and the phase change QPH, that is mass into HFG, and this relation QSH, that is temperature required to raise the temperature of steam from the boiling point to the desired superheated temperature. That is, we first come from the initial stage to the boiling stage, from the boiling to the superheated point. So we will use these relations to calculate the final total heat. So for sensible heating system, so we have QS is equal to M into CPL in the difference of T boiling minus T initial. So this is equal to 2 into 4.18 into boiling temperature of water is 100, initial temperature is given 45 degrees. This is equal to 459.8 kilojoules. Then we have phase change, because it changes from liquid to gas now. Now Q for phase change, that is given here, mass into the enthalpy. Q for phase change, this is equal to mass into HFG. Mass is 2 kilograms and HFG value is 2257 kg per kilogram. So therefore phase change value here turns out to be 4514 kilojoules of heat. So this is phase change. Next, when we talk about superheating system, for a superheating system, Q for superheating, SH superheating, this is equal to M times CPS into TF minus T boil. This is equal to 2 into value of CPS is 2 kilojoules per kg into the final temperature minus boiling temperature. Final temperature is 300 degrees, boiling temperature is 100. This value turns out to be 800 kilojoules. Now total heat, because they asked about total heat that is there, it is Q is equal to QS, that is heat required to raise temperature of the liquor from its initial temperature to boiling. This is up to boiling. This plus Q pH. This is for phase change plus Q SH. This is for superheating. So putting all these values, QS is 459.8 kilojoules, QPH is 4514 kilojoules plus Q superheating, that is 800 kilojoules. Now you can see here heating from the initial temperature to the boiling temperature is heat required, that is 459.8 kilojoules of heat. When we change phase or when the phase is changed, the heat required is quite high. It is around 10 times of what is required from the initial to the boiling temperature. Initial temperature was 45 degree, boiling temperature was 100 degree only. So at 100 degrees, this much amount of heat is there. But there when 100 degree phase change has happened, after the phase change, heat required is also much lesser than what is required for the phase change. From 100 degree to 300 degrees, this much of heat is required. This total turns out to be 577.3.8 kilojoules of heat. It is the total heat. So here it takes Q is equal to 577.8 kilojoules. This is my answer. With this, I am closing the lecture on psychrometrics, which is the study of the water vapor. We try to talk about phase change, we try to talk about the dryness factor and many other things. We have discussed only very trivial problems. If you wish to discuss or practice it further, use the reference books which are given in the course homepage, practice your own problems, and if you face any challenge there, put the question in the forum. We will try our best to answer your queries. Thank you.